All right, let's kick off this deep dive with something kind of fascinating, maybe a bit counterintuitive about your own body. Did you know that right now, listening to this, you are technically, well, a little bit basic?
Uh, yeah, that's right. Chemically speaking, anyway.
Right, your blood pH puts you just, ever so slightly on the alkaline side, exactly where it needs to be.
It's this really subtle but absolutely profound balancing act happening inside you constantly, every second.
So today, we're plunging into that world. The world of pH, literally the power of hydrogen, and why it's just so critical in our biology.
hmm And we should probably also clear up some of the confusion around organic and inorganic molecules, too.
Oh, definitely. Because the chemistry definition, well, it might surprise you compared to what you hear about, like, organic food.
Exactly. Not the same thing at all.
So our mission, our goal for this deep dive is really to unpack these core ideas, pH, acids, bases, these molecule distinctions. We want to give you a clear, sort of concise handle on why these invisible forces are just so vital for life itself.
Yeah, get ready to really understand what's going on inside you at that molecular level.
And why these tiny little players are actually such a huge deal.
It's truly remarkable, isn't it? How something as simple, almost fleeting, as a single hydrogen ion, just a proton, really underpins this whole symphony of biological processes. It's this constant microscopic balancing act, just for us to exist.
Wow. Okay, so where do we start? pH itself.
Yeah, let's start there. Simply put, pH is a measure of the relative concentrations of hydrogen ions, H plus, area, and these other things, hydroxide anions, OH, in a solution. It's basically how we quantify how acidic or how basic something is.
Okay, so it's all about these tiny ions floating around, but that scale, the pH scale, it always felt a bit backwards to me. Like more H plus ions, which you'd think makes something stronger acidically, actually means a lower pH number.
That's a really common point of confusion, yeah. But you've got it exactly right. It's an inverse relationship. More H plus ions mean a lower pH. That means more acidic.
Okay.
And conversely, fewer H plus ions mean a higher pH,
Hmm.
more basic or alkaline.
So where do the OH ions fit in? You mentioned them too.
Right, the hydroxide ions, they kind of move in the opposite direction on the scale.
Yeah.
If you have more OH ions, that drives the pH higher because they effectively grab onto the free H plus ions, taking them out of the equation, so to speak.
Okay, so it is like a seesaw. More H plus means less effective OH, lower pH. More OH means less effective H plus I, higher pH.
Precisely. And the scale finds its perfect balance point right in the middle at a neutral pH.
Which is 7.0.
Exactly. Like pure water. That's where the H plus and OH ions are in perfect equilibrium. Equal concentrations.
Got it. So logically then, anything with a pH lower than 7.0 is acidic. That means it has, relatively speaking, a high concentration of H plus and a low concentration of OH.
Perfect.
And then if the pH goes above 7.0, that's what we call basic or alkaline, which signifies a low H plus concentration and therefore a higher OH concentration.
You've nailed it. It's all built on those precise ratios.
Okay, that makes sense.
And this naturally leads us to the chemical definitions of acids and bases themselves. An acid fundamentally is what we call an electrolyte, meaning it's a substance that dissociates in solution, forms ions, lets electricity conduct, and crucially, when it dissociates, it releases hydrogen ions. Those H plus ions we keep talking about, they're H plus donors.
H plus donors. Okay, so acids are giving away protons. Does that connect to, why strong acids taste sour or can be corrosive? Is that the giving away part?
That's often related, yeah, especially the reactivity part for strong acids,
Oh.
though the mechanism is a bit more complex than just giving away.
And bases then? Are they just the opposite, the takers?
Essentially, yes. Bases are substances that release ions, which readily combine with those hydrogen ions. They mop them up, so in effect, they act as H plus acceptors. They remove the free hydrogen ions from the solution.
Okay, donors and acceptor.
And this intricate exchange, this donating and accepting, is absolutely fundamental to how pH changes are managed, especially inside your body.
Right, bringing it back to us. You mentioned our blood pH earlier. It's kept in that super narrow range, 7.35 to 7.45.
Incredibly narrow, yes.
Which confirms that slightly basic status we talked about at the start. And you also mentioned something important. pH specifically measures the free H plus ions, right? Not just all the hydrogen atoms hanging around.
Absolutely. Critical point. It's only the unbound, free-floating H plus ions in the solution that contribute to the pH measurement. The body is laser focused on those active ions.
Okay. and maintaining that narrow 7.35, 7.45 range. It's not just important, it sounds like it's life or death.
It absolutely is.
Mm.
If you have too many free H plus ions, so the pH drops too low, that condition is called acidosis, and it's incredibly dangerous. Even a small drop below that 7.35 can start to damage cells and tissues.
What does it actually do?
Well, a key thing is it starts to alter the structure of vital proteins, including enzymes. It causes them to denature, essentially unravel or change shape.
Mhm.
And if proteins change shape, they can't do their jobs. It messes up everything: nerve signals, muscle contractions, metabolism, nearly every physiological process.
Wow, that's not just dangerous, it's like throwing a wrench into the entire body's molecular machinery, just completely disrupted.
Exactly.
So, what about the other way? What happens if your pH goes too high? Too many OH ions, not enough H plus Ga.
That condition is alkalosis, and it can be just as alarming, maybe even more immediately dramatic sometimes.
Really? How so?
While acidosis tends to, depress function, slow things down, alkalosis can lead to overexcitability of the nervous system. In the blood, a high pH can trigger things like uncontrollable, sustained skeletal muscle contractions.
You mean like cramps?
Yeah.
But everywhere, all at once?
Potentially, yes. Severe spasms, tetany, even seizures in extreme cases. Imagine your muscles just locking up involuntarily.
Yikes. Okay, that really drives home why this balance, this pH homeostasis, is so incredibly vital. It's not just about feeling good, it's about basic function, preventing total system breakdown.
Precisely.
So given how disastrous things get if it goes wrong, how does the body possibly manage to keep such tight control? That's where buffers come in, isn't it? Are they
Yeah.
like the body's chemical shock absorbers?
It's a perfect analogy. Chemical shock absorbers. Given how critical that narrow pH window is, the body needs an immediate, robust defense system. That's the job of buffers. They're typically compounds made of a weak acid and its related salt.
Weak acid. Why weak?
Ah, that's the clever part.
Mhm.
Because they're weak, they don't fully dissociate in water. This means they exist in a sort of equilibrium. They can release H plus ions if the environment gets too basic, or they can absorb excess H plus ions if it gets too acidic.
Oh, I see. So they can kind of swing both ways depending on what's needed.
Exactly. Their brilliance lies in that dual ability. They can neutralize either incoming strong acids or strong bases that might show up, perhaps from metabolism or diet. They resist those drastic, potentially lethal pH shifts.
So it's like our body has this amazing internal SWAT team, constantly managing the chemical environment. It makes you wonder if someone, say, drinks something acidic, like lemon juice. Does the body even flinch? Or are those buffers just instantly on the job?
For normal dietary things, yeah, the buffers are incredibly effective.
Yeah.
They handle typical fluctuations without you ever noticing a change in your blood pH. They absorb the shock, like you said.
But is there a limit? Can they get overwhelmed?
Absolutely. There is a limit to their capacity.
Yeah.
Think about serious conditions like kidney failure, where the body can't excrete acids properly, or uncontrolled diabetes, which can produce a lot of acidic ketone bodies.
Yeah.
In those situations, the buffer systems can become overwhelmed.
And that's when you actually see the dangerous shifts into clinical acidosis or alkalosis.
Precisely. That's when medical help becomes essential, because the body's own defenses are being pushed past their limit. It's a powerful system, but it's not infinite.
That's a really crucial point. They work hard, but they're not invincible. Okay. Now, we've talked a lot about these tiny ions, H plus and OH, but what about the bigger building blocks? There's this other area where chemistry definitions can really clash with everyday language, especially around food. Organic versus inorganic.
Yes. This causes so much confusion. It's a really important distinction in chemistry, and it often gets blurred. So let's be clear. In chemistry, for a compound to be classified as organic, it absolutely must contain carbon. C, bonded directly to hydrogen, H.
Carbon bonded to hydrogen, that's the rule.
That's the fundamental rule. These carbon-hydrogen bonds often form the backbone, the skeleton of complex chains and rings. These are the structures that make up life's essential molecules: proteins, carbohydrates, fats, DNA.
Okay, so if it doesn't have that specific carbon-hydrogen bond structure, even if it contains carbon, it's generally considered inorganic.
That's usually the case, yes. Inorganic compounds generally do not contain C and H atoms as their primary structural feature.
What are the most important inorganic compounds in our bodies, then?
Well, they're incredibly familiar, even vital. Water, H2O for starters, oxygen gas, O2, carbon dioxide, CO2, and also various inorganic acids, bases, and salts, like sodium chloride, table salt.
Wait, CO2, carbon dioxide has carbon, but you're saying it's inorganic.
Correct. And that's a perfect example of the rule.
Hmm.
CO2 has carbon and oxygen, but it lacks that direct carbon to hydrogen bond. It also doesn't form those complex chains and rings characteristic of organic molecules. So chemically, it's classified as inorganic.
Ah, okay. It's about the type of bonding and structure, not just the presence of a carbon atom. That clarifies things a lot.
Exactly. It's a structural definition in chemistry.
All right, so let's maybe do a quick recap. We've dug into pH, that measure of relative H plus and OH concentrations. We saw how the scale works, that inverse relationship, and why neutral is 7.
And we defined acids as those H plus donors or releasers
Yeah.
and bases as the H plus acceptors, the ones that combine with hydrogen ions.
And we really hit home how critical that super narrow blood pH range, 7.35 to 7.45, actually is.
Yeah, with acidosis being too low, potentially denaturing proteins, and alkalosis being too high, causing things like muscle contractions, both very dangerous.
And the body's defense, buffers, those weak acid-salt compounds acting as chemical resistors fighting to keep things stable.
Absolutely. And then we cleared up the organic versus inorganic distinction. Organic chemistry is a chemistry of compounds containing carbon bonded to hydrogen, while inorganic compounds generally lack that CH bond structure, even if they include vital things like water, oxygen, and CO2.
It really puts things into perspective, all these, invisible forces and microscopic ions constantly working away inside us.
Maintaining these incredibly delicate balances that are just essential for every single thing our bodies do.
Yeah, and most of the time, we don't have a clue what's even happening.
It just works until it doesn't.
So, maybe a final thought for everyone listening. As you go about your day, just, consider this. These seemingly abstract ideas, tiny ions, specific chemical bonds, they aren't just stuff you learn in a textbook.
Not at all. They are actively, right now, maintaining the incredibly delicate balance inside you, the balance that lets you live, think, move.
Yeah. This dive into the microscopic really shows how these, well, fundamentally simple chemical principles underpin the staggering complexity of life itself.
Keeping you right in that sweet spot, that slightly basic state, right down to your very cells. Pretty amazing.
Absolutely amazing.